Welcome to this beginner-friendly tutorial on neural networks. Before we get started, make sure you have both Python and PyCharm installed on your computer. Python is the programming language we will use, and PyCharm is the development environment where you will write and run your code. Now, let's talk about what a neural network actually is. You can think of a neural network as a collection of layers stacked together. Each layer is made up of many small units called neurons. A neuron is like a tiny calculator. It multiplies the inputs by weights, adds a bias, and then decides whether or not to activate. This activation is a signal that gets passed forward to the next layer. At the beginning of a network, the input layer takes in raw information, like numbers, images, or text. Hidden layers sit in the middle, processing and transforming that information step by step. Finally, the output layer produces the answer, such as predicting a number, identifying an object, or classifying text. The strength of neural networks comes from having many layers working together, where each neuron contributes to recognizing patterns, just like how our brains work with interconnected cells. Think of it like a dimmer switch controlling a light. Instead of just on or off, each neuron decides how strongly it should pass its signal forward. The combination of all these tiny decisions across many neurons and layers allows a neural network to make surprisingly complex judgments. Once you are ready, open PyCharm and click on New Project to begin setting up your workspace. Name the project Intro to Neural Network and click Create. The project is your workshop where all code and experiments will live. Right-click the project folder. This is like opening a binder where you will add new pages for your code files. Point to New to create a new item in the project. It is like adding a fresh sheet of paper to your binder. Click Python File so PyCharm wires the file to your interpreter. This makes the file easy to run and debug. Name the file Neural Intro and press Enter. Clear names are like labels on storage bins and make code easy to find later. Here is what you will build. 1. A 1D Neuron Explorer where you change weight, bias, and input to see how output changes. 2. A 2D Linear Classifier that draws a decision line between two groups. Picture volume knobs and a straight fence that separates two fields. Import sys so your program can talk to the Python runtime. It gives access to exits, command line args, and clean shutdowns. Think of it as the building control panel. Import NumPy as NP for fast math on arrays. NumPy acts like a power calculator that handles whole columns of numbers at once, similar to a spreadsheet formula that fills a column instantly. In this step, we are preparing our project by importing the tools we will need. First, we bring in NumPy, a library that makes working with numbers and arrays simple and efficient. Next, we import PySide6, which is a framework that allows us to create graphical interfaces. With PySide6, we can design windows, buttons, labels, and layouts that make our neural network app interactive and easy to use. Think of NumPy as the engine that handles the math, while PySide6 is the toolbox that helps us build the dashboard where users can interact with the math visually. By combining these two, we can simulate how neurons behave, and at the same time give users sliders, buttons, and graphs to explore the results. This setup is the foundation. Without these imports, our application would not know how to handle the calculations or how to display anything on the screen. Here we bring in Matplotlib, the library that lets us draw charts and graphs. To make these graphs appear inside our PySide6 application, we use the QDAG backend, which acts as a bridge between Matplotlib and the PySide6 framework. We also import the figure class. You can think of a figure as a blank canvas, like a whiteboard, where we will draw neurons, decision boundaries, and data points. Together, these tools give our neural network app the ability to show visual feedback. As you adjust weights or biases, the math behind the neuron will instantly be drawn on this canvas. That way, you can clearly see how the decisions of a neuron change in real time. At this point, we are defining our very first activation function. An activation function is the decision maker inside a neuron. It looks at the input value, called z, and then decides what signal to pass forward. The function here is called actLinear, which simply returns the same value it receives. This is known as a linear activation. You can think of it like a clear glass window. Whatever light comes in is exactly what goes out, without any filtering or distortion. While this function might seem simple, it's an important building block. Later, we will introduce other activation functions, such as sigmoid or ReLU, which bend or shape the output in different ways. These different shapes are what allow neural networks to capture complex patterns and make better predictions. Now we are adding another activation function called the sigmoid function. Unlike the linear function we saw earlier, the sigmoid does not simply pass values straight through. Instead, it squeezes any number into a smooth curve that always falls between 0 and 1. You can think of it like a soft dimmer switch. If the input is very negative, the output is close to 0, meaning the neuron is almost turned off. If the input is very positive, the output is close to 1, meaning the neuron is strongly activated. Values in the middle get mapped to a gradual slope between those two extremes. This is powerful because it allows neurons to make probability-like decisions. For example, in a classification problem, the sigmoid function can tell us how likely it is that something belongs to a certain category, such as whether an image contains a cat or not. Next, we are adding another important activation function called ReLU, which stands for Rectified Linear Unit. Unlike the sigmoid that smoothly curves between 0 and 1, ReLU has a very simple rule. If the input is negative, the output is 0, but if the input is positive, the output is just the same value. You can picture this like a one-way valve. Negative values are blocked completely, while positive values pass through without being changed. This makes ReLU very efficient and one of the most widely used activation functions in modern neural networks. Its strength is that it introduces nonlinearity, allowing networks to learn complex patterns while still being computationally fast. That is why you will often find ReLU at the core of deep learning models, especially in image recognition and natural language tasks. We now introduce another activation function called tanh, which stands for hyperbolic tangent. This function is similar to the sigmoid function, but instead of squeezing values between 0 and 1, it compresses them into a range between -1 and +1. You can think of it like a balanced scale. If the input is strongly negative, the output leans toward -1. If the input is strongly positive, the output leans toward +1. And when the input is near 0, the output settles somewhere in the middle. This balance around 0 often makes the tanh function more effective than sigmoid in practice, especially when training deeper networks, because it helps the neurons learn both positive and negative relationships. It gives the model more flexibility in recognizing patterns. At this stage, we are organizing all of our activation functions into a single dictionary called activations. This dictionary works like a quick reference guide, letting us choose an activation function by name instead of having to call the function directly every time. For example, if we want to use the sigmoid function, we can simply look up sigmoid in the dictionary, and it will return the correct function to run. The same goes for tanh, ReLU, and linear. This setup is powerful because it makes our code flexible. Instead of being locked into a single activation, we can easily switch between them when testing how different neurons behave. Think of it like a toolbox, where each tool has a label: hammer, wrench, screwdriver, and you just grab the one you need without confusion. By storing all the activations in one place, we are making the neural network easier to extend, experiment with, and maintain. Here, we are creating a special class called PL-Canvas, which will act as the drawing board for our graphs. This class is built on top of Matplotlib's figure canvas, which lets us display plots inside our PySide6 application window. Inside the class, we set up a figure, which is like a blank sheet of paper, and then add a subplot, which is the actual area where graphs will be drawn. We also configure the canvas to expand and fit nicely into the application layout, so no matter how you resize the window, the graph adjusts automatically. Think of this as setting up the stage for a play. The figure is the stage itself, the subplot is where the action happens, and the canvas makes sure the stage is always visible, whether the window is small or large. This foundation is essential because later we will use it to visualize how neurons respond to different inputs and how decision boundaries shift in real time. Now we are introducing a new class called Single Neuron Widget. This will be the building block of our app that represents a single neuron on the screen. By using PySide6's QWidget, we can create a container that holds everything related to one neuron, such as its inputs, weights, bias, and output. Think of this widget as a small interactive panel. Later on, it will let us adjust values like the bias or activation type, and immediately see how the neuron responds. Just like in a real neural network, each neuron plays its part, and when many are combined, they work together to solve complex problems. This is the first step toward connecting the math we wrote earlier with the visual interface that the user can interact with. Here we are expanding the single neuron widget class to make it functional. This widget now takes in an input value, a weight, a bias, and lets us choose which activation function to apply. In simple terms, it is the digital version of a single neuron. Inside the code, the neuron is defined as the equation y equals activation of w times x plus b. That means we multiply the input by the weight, add the bias, and then pass the result through whichever activation function we select: linear, sigmoid, ReLU, or tanh. The widget also places a marker on the graph so we can see exactly how the current input behaves. This makes it very visual. Instead of just doing math behind the scenes, we can actually watch the neuron's output change as we adjust its values. Think of this widget as a microscope. It zooms into one single neuron, showing us how it responds, before we later connect many neurons together to form a full neural network. We are now starting to build the user interface for the neuron widget. The method being added, called buildUI, creates the layout that will hold all the interactive elements of our single neuron. Here, we use a vertical box layout, which means everything we add to the widget will be stacked neatly from top to bottom. Later on, this layout will include controls like sliders, input boxes, and labels that let us adjust the neuron's weight, bias, and activation function. Think of this as setting up the shelves in a cabinet. Once the shelves are in place, we can start filling them with items. In this case, the interactive tools that bring our neuron to life. By separating the layout into its own method, we also keep the code clean and flexible, making it easy to expand the interface with new components later. Now we are adding the controls group to our neuron widget. This is where we will place all the interactive tools, like sliders, drop-down menus, and buttons, that let us adjust the neuron's behavior. We create a QGroup box called Controls, which acts like a labeled container. Inside it, we use a grid layout to neatly organize everything in rows and columns. This approach makes sure the interface stays clean and easy to use, even as we add more options. Think of this like setting up a control panel for a machine. Each knob, switch, or slider will soon let us fine-tune parts of the neuron, such as the weight, bias, and activation function, and instantly see the results on the graph. At this point, we are adding the activation selector to our neuron widget. This is a drop-down menu, also called a combo box, that lets the user choose which activation function to apply to the neuron. Inside the code, we fill the menu with all the activation options we created earlier: linear, sigmoid, ReLU, and tanh. When the user changes the selection, the program automatically updates the plot, so you can immediately see how the neuron's behavior changes with the new activation. Think of this like switching lenses on a camera. Each lens gives you a different perspective on the same scene. In the same way, each activation function transforms the input in its own unique way, helping the neuron capture different patterns. This control makes experimentation easy because you can quickly compare how each activation function responds to the same input. Here we are adding the knobs and spin boxes that let us fine-tune the values of the neuron, specifically the weight, the bias, and the input. The dials act like larger, more interactive controls that you can turn, while the spin boxes give you precise numeric adjustments. Together, they provide both quick changes and fine-grained control. For example, turning the weight dial is like adjusting the volume knob on a speaker. It changes how strongly the input influences the neuron. The bias dial shifts the output up or down, much like moving the baseline of a graph. And the input dial lets you set the value that flows into the neuron so you can immediately see how the output responds. These controls make the abstract math of y equals activation of w times x plus b come alive, because you can visually explore how each part of the equation affects the neuron's behavior. Here we are connecting the dials and the spin boxes so that they stay in sync. This means whenever you adjust a dial, the corresponding spin box updates automatically, and when you change the spin box value, the dial also moves to match. This synchronization is important because it combines two ways of controlling the neuron. Dials give a smooth, intuitive feel, while spin boxes allow precise numeric entry. By linking them together, we get the best of both worlds: quick adjustments with accuracy. Think of it like having both a steering wheel and a GPS for your car. The steering wheel lets you guide freely, while the GPS gives you precise numbers for distance and direction. Both are useful, and when they agree with each other, the experience is smooth and reliable. This step ensures that the neuron's controls are consistent, making it easier for users to experiment without confusion. Here we are adding two buttons to the Neuron widget: Reset and Randomize. The Reset button brings everything back to its default state. That means the weight, bias, and input all return to their starting values, making it easy to start fresh if you've been experimenting. The Randomize button gives each value a new random setting. This is especially useful for exploring different neuron behaviors quickly without having to manually adjust the controls. Think of these like shortcuts. Reset is the undo button that clears the slate, and Randomize is the shuffle button that surprises you with a new setup. Both are helpful when testing because they let you explore how neurons behave under different conditions without extra effort. In this step, we are arranging all of the controls neatly into the grid layout so the interface looks organized and easy to use. Each row of the grid has a clear purpose. The first row is for the activation selector, letting us pick which activation function the neuron uses. The second row holds the controls for the weight, with both the dial and spin box side by side. The third row is for the bias, and the fourth row is for the input value. Finally, the last row contains the Reset and Randomize buttons, so we can quickly restart or experiment with new values. Think of this like building the dashboard of a car. The speedometer, fuel gauge, and controls aren't just thrown around randomly. They're placed in an orderly way so the driver can easily see and adjust them. In the same way, this grid layout ensures that all neuron controls are grouped logically, making it simple for the user to experiment without confusion. This step adds the plot area where the neuron's output will be displayed visually. The plot is created using our custom Matplotlib canvas, and then it is added directly to the widget's layout. Think of this as setting up the screen on a scientific calculator. All the controls, the weight, bias, input, and activation selector, let us change the numbers, but the plot is where we actually see the results drawn in real time. By having this canvas inside the widget, the user can watch how the output curve changes instantly whenever a control is adjusted. This makes the connection between the math equation y equals activation w times x plus b and its graphical behavior crystal clear. To finish setting up the Neuron widget, we add labels that display the equation and the numeric outputs. The equation label shows the formula the neuron is using, like y equals activation w times x plus b, so the user always sees the math behind the visuals. The values label shows the current calculated numbers based on the weight, bias, and input that are selected. These labels make the experience more transparent. Instead of just adjusting dials and looking at a graph, the learner can see the exact formula being applied and the precise output values. It's similar to having subtitles on a video. You don't just watch what's happening, you also see the explanation in text. This dual representation, both visual and numeric, helps solidify the connection between the math and the behavior of the neuron. At this point, we are creating a helper method called makeDial. This method builds the circular dials we've been using for weight, bias, and input. Each dial is set up with a range that goes from -500 to +500, giving plenty of room for adjustments. The code also makes sure the dial looks and feels like a proper knob. It has notches to guide movement, a sensible step size so the changes aren't too jumpy, and a minimum size so it's easy to grab and control. Finally, whenever the dial's value changes, it triggers an update to the plot, so the graph always reflects the latest adjustment. You can think of this dial like the tuning knob on an old radio. Turning it smoothly moves you across frequencies, and the graph is like the sound that updates instantly to show whether you're in tune or not. Now we are creating another helper method, this time called makeSpinBox. A spinbox is a small numeric control that lets the user type in or click arrows to adjust a value precisely. In this setup, the spin box is given a range from -5 to +5, with small step increments of 0.01 and support for 2 decimal places. That means users can fine-tune the weight, bias, or input value with much greater accuracy than with the dials alone. Whenever the value changes, the plot is refreshed so the graph always shows the updated result. Think of this spin box as the fine adjustment knob on a microscope. The dial gives you the big movement, but the spin box lets you carefully focus in and lock onto the exact detail you want. What we're adding here are utility methods that keep the dials and spin boxes working together smoothly. The methods dial to float and float to dial act as translators. The dial internally works with large integer values, while the spin box expects decimal numbers like 0.25 or -3.40. These two functions make sure we can move back and forth between those formats. Without them, the dial and spin box wouldn't agree on the same value. On top of that, we have the sync methods, score sync from dial and sync from spin. These are responsible for updating one control whenever the other changes. If you turn the dial, the spin box updates. If you type into the spin box, the dial moves to match. This two-way synchronization ensures consistency. You can think of it like having both an analog speedometer and a digital speed readout in a car. One is a needle, the other is a number, but they both must show the same speed. The conversion methods make sure the units match, and the sync methods keep them updated in real time. Instead of pulling values directly from the UI every time, we now define small functions called state accessors. These act as shortcuts that neatly return the neuron's current settings. The methods W, B, and X return the weight, bias, and input value. The method activation name tells us which activation function is currently selected, and activation gives back the actual function itself from the activation dictionary. By organizing them this way, the rest of the program can treat the neuron like a simple object with properties, without worrying about where those values come from in the interface. It's like asking a librarian for the right book instead of digging through the shelves yourself. The accessors handle the details, so the rest of the code stays clean and focused. This separation also makes it easier later on to expand or modify the UI, since the rest of the application only needs to call these accessor methods, not touch the widgets directly. At this stage, we're adding two important methods that control the starting point and variability of the neuron: set defaults and randomize. The set defaults method initializes the neuron with clean, predictable values for weight, bias, and input. It also sets the default activation function to sigmoid. This is useful for demonstrations or screenshots because it always starts the neuron in a consistent state. The randomize method, on the other hand, generates random values for weight, bias, and input within a given range. This mimics what happens in real neural networks, where neurons usually start with random weights before training begins. By adding randomization, we make it easy to explore different configurations quickly without manually changing each control. Think of it like two buttons on a lab experiment. One that resets everything to a standard setup, and another that shakes things up so you can test different conditions. Together, they give the learner both stability and flexibility. We now begin defining the update plot method, which is responsible for refreshing the neuron's graph whenever something changes. The first action inside this method is to clear the existing plot so that old lines and markers don't overlap with the new ones. This is important because every time we adjust a weight, bias, or input value, or switch the activation function, the visualization needs to show only the most recent result. Without clearing it first, the plot would quickly become cluttered and confusing. Think of it like wiping a whiteboard clean before drawing a new diagram. Clearing the canvas ensures that what we see is always current and easy to interpret. The next part of the update plot method is where the neuron's curve actually gets calculated. First, we generate a range of input values called XS, which go from -5 to +5. These act as the possible inputs we want to test. Then we compute Z, which is the weighted sum of those inputs plus the bias. After that, we pass Z through the currently selected activation function to get Y, the neuron's final output. In simple terms, this is like taking a recipe. XS are all the ingredients you try, W and B adjust the proportions, and the activation function is the cooking method that transforms them. The result y is the neuron's unique flavor, ready to be plotted on the graph. The main curve of the neuron is now drawn on the graph. Using the excess inputs we generated earlier and the corresponding outputs y, the code calls ax.plot to create a smooth line. The line width parameter is set a little thicker so the curve is easy to see. This is the visual heartbeat of the neuron. As the weight, bias, or activation function change, the shape of this curve changes too, showing how the neuron transforms inputs into outputs. It's very much like plotting a road map. The inputs are the path along the x-axis, the outputs are the height along the y-axis, and the curve is the journey that connects them. Watching this line shift in real time makes the math of neural networks come alive. In this step, we highlight the specific input and output point of the neuron on the graph. The code calculates z0, which is the weighted sum of the chosen input plus the bias. Then it passes z0 through the activation function to get y0, the actual output at that point. Next, a scatter marker is drawn at the exact input-output position, making it easy to see where the neuron is firing. To make it even clearer, a vertical and a horizontal dashed line are added, connecting the input on the x-axis to the output on the y-axis. This creates a visual guide that shows not only the overall activation curve, but also how one specific input flows through the neuron to produce a result. It's like plotting a single test point on a machine's performance curve so you can see exactly how it behaves under current settings. To finish off the visualization, we add labels and a title to the graph. The x-axis is labeled as input x, the y-axis is labeled as output y, and the title shows the full formula of the neuron, including the name of the activation function currently selected. This small detail makes a big difference for learners. By looking at the graph, they immediately know what the axes represent and which activation function is being applied. It ties the visual curve back to the math formula y equals activation w's x plus b in a clear and direct way. It's similar to reading a chart in a science textbook. The labels and title guide your interpretation, making sure you understand not just the picture, but also the meaning behind it. At this point, the code is making the graph easier to read by adjusting the y-axis limits dynamically. Different activation functions behave differently, so the graph needs to adapt. For example, the sigmoid function always produces outputs between 0 and 1, so the y-axis is set to stay in that range. The root function, on the other hand, can shoot up very high, so the code limits the window to keep it visible and understandable. Other activation functions, like tang or linear, get their own sensible ranges so the graph never looks squished or stretched too far. Finally, a grid is added and the canvas is redrawn, giving the visualization a polished, professional look. Think of this as adjusting the frame around a picture so the most important details are always centered and easy to see. This step updates the labels that appear under the neuron widget so the math and the current values are shown clearly to the user. First, the equation label is set to display the general formula of the neuron, z equals w times xb and y equals activation z. Then, a second label is updated with the actual numeric values in real time. It shows the current weight, bias, and input, along with the calculated z and the resulting output y. This is powerful because it bridges the gap between theory and practice. Instead of only seeing a formula, the learner can watch the numbers update as they move the dials or type into the spin boxes. It's like doing a math problem on paper, but having the calculator instantly show the result alongside the equation. Now we are moving beyond a single input neuron and introducing a 2D linear classifier widget. This new widget represents a neuron that takes two inputs with two weights, W1 and W2, and a bias B. The purpose here is to visualize how a neuron can create a decision boundary in 2 dimensions. For example, it can separate data points into 2 groups using a straight line. This allows us to explore simple synthetic datasets, like ones that can be separated with a line, and also more challenging ones, such as XOR, where a single neuron isn't enough. This is a big step forward because it shows both the strengths and the limitations of a single linear neuron. It's like giving the neuron a bigger playing field. Instead of drawing a line on a number line, it's now drawing a line across a full 2D plane. In this step, we initialize the 2D linear classifier widget. The constructor sets up everything the widget needs to function. It starts by calling the parent class initializer to ensure the base behavior is ready. Then, it creates a random number generator with a fixed seed so that the results are reproducible each time the program runs. After that, the code builds the user interface, prepares the first dataset, which in this case is a simple linearly separable set, and finally applies default values before updating the plot. You can think of this initialization like preparing a laboratory experiment. The parent setup is turning on the lab equipment. The random number generator ensures consistent test conditions. The dataset provides the sample material, and the defaults give a clean starting point. Once everything is ready, the plot shows the neuron's decision boundary on the screen. In this step, we begin building the user interface for the 2D classifier widget. A vertical box layout is created to act as the main container for all of the components that will be added later. This layout will allow us to stack controls, plots, and labels in a clean and organized way. Think of this as setting up the frame of a house. Before adding rooms, furniture, or decorations, we first need a solid structure to hold everything together. In the same way, this root layout gives us the foundation for arranging the neuron's controls and visualizations. At this point, the controls section for the 2D classifier widget is being set up. A group box labeled Classifier Controls is created to hold all the interactive elements, and inside it, a grid layout is used to neatly organize them. The group box acts like a container with a title, making it clear to the user that everything inside belongs to the classifier settings. The grid layout ensures that future controls, such as sliders, spin boxes, or drop-down menus, will line up in an orderly way, making the interface easy to use. It's similar to adding a labeled control panel on a machine. The frame and layout don't do anything by themselves, but they provide structure so all the buttons and switches can be placed in the right spots. Now we're adding a dataset chooser control to the 2D classifier widget. This is a combo box that lets the user pick which dataset they want to experiment with. The available options are a linearly separable dataset, an XOR dataset that cannot be separated by a single line, and a noisy blobs dataset that introduces randomness. Whenever the user switches the dataset, the program automatically updates by connecting the combo box to the dataset change function. This way, the visualization and decision boundary immediately reflect the chosen dataset. You can think of this as selecting different training grounds for the neuron. Each dataset presents a unique challenge, showing both what a single neuron can handle and where it struggles. In this step, we add controls for adjusting the two weights and the bias of the 2D classifier. Just like with the single neuron widget, each parameter has both a dial for smooth adjustments and a spin box for precise numeric entry. The code also connects the dials and spin boxes so they stay synchronized. That way, if you turn a dial, the number in the spin box updates, and if you type in a new number, the dial moves to match. This gives the learner two different ways to explore how the decision boundary changes: a hands-on, intuitive feel with the dials, and an exact, controlled adjustment with the spin boxes. You can imagine it like tuning an instrument. The dials are like adjusting the string tension by hand, while the spin boxes are like using a digital tuner to hit the exact pitch. Together, they make experimenting both fun and accurate. Now we add extra controls to make the 2D classifier more interactive. Two buttons are created, one for reset, which returns all values to their defaults, and another for randomize, which generates new random weights and bias so you can quickly test different decision boundaries. Alongside the buttons, a label called accuracy is introduced. This will later be used to show how well the neuron performs on the selected dataset. By updating this label dynamically, the learner can see in real time how adjusting weights and bias affects the classifier's ability to separate the data correctly. Think of reset and randomize as quick tools in an experiment. One gives you a clean slate, and the other shakes things up. The accuracy label acts like a performance meter, telling you instantly how well the model is doing under the current settings. This step organizes all of the classifier controls into the grid layout so they appear in a clear, structured way. Each row of the grid has a specific purpose. The first row is for selecting the dataset. The next two rows allow adjustment of the weights, W1, which influences the x-axis direction, and W2, which influences the y-axis direction. The following row is for the bias, which shifts the decision boundary up or down. Below these controls, the Reset and Randomize buttons are placed side by side, giving quick access to start fresh or explore new configurations. Finally, the Accuracy label is added, which will later show how well the classifier performs on the chosen dataset. Think of this grid like the dashboard of an aircraft. Each control has a dedicated spot, making it easy to read, adjust, and monitor performance in real time. At this stage, the plot canvas is added into the 2D classifier widget, so the decision boundary can be drawn right alongside the controls. The canvas is created with a fixed size and resolution, then added into the layout to become part of the interactive interface. By embedding the plot directly in the widget, every adjustment to the weights, bias, or dataset will instantly be reflected in the visualization. It transforms the abstract math into something visual and dynamic, helping learners see how the classifier works in real time. It's like installing the screen on a scientific instrument. The knobs and switches are useful, but the real value comes from watching the output update live on the display. At this point, we define two helper methods, make_dial and make_spinbox, for the 2D classifier. These are the same building blocks we used in the single neuron widget, but are now reused to handle the new parameters of the classifier. The dial provides smooth, intuitive adjustments with a large range, while the spinbox allows precise numeric input with small increments and decimal precision. Both controls are linked to automatically trigger updates to the plot whenever their values change. Together, these helpers make it easy to create consistent, reusable controls for weights and bias across different widgets. It's like designing a standard set of knobs and sliders for a soundboard. You can reuse them for any track, knowing they'll behave in a reliable way. Now we introduce conversion and synchronization helpers for the 2D classifier controls. The methods dial to float and float to dial act like translators, converting between the dial's integer values and the spinbox's decimal values. Without this translation, the two controls wouldn't agree on what number they're representing. On top of that, the sync methods, sync from dial and sync from spin, keep the controls in step with each other. If you turn the dial, the spinbox updates automatically. If you type in the spinbox, the dial moves to match. This design ensures consistency and a smooth user experience. It's like having both an analog gauge and a digital readout on a machine. They may look different, but they always display the same measurement because they're synchronized behind the scenes. Here we define the onDataset change method, which makes the widget respond when the user selects a new dataset from the drop-down menu. The function takes the dataset name, prepares the dataset accordingly, and then updates the plot so the visualization matches the new choice. This step is what makes the dataset selector interactive. Without it, changing the option in the combo box would not affect what is shown on the screen. It's like flipping a switch on a lab experiment to use a different sample. As soon as the switch is flipped, the setup updates automatically, giving the learner immediate feedback on how the classifier performs on the new dataset. Now we define the prepare dataset method. This function is responsible for setting up the actual data points that the classifier will try to separate. It takes in the name of the dataset selected by the user and generates the corresponding input values and labels. Different datasets highlight different strengths and weaknesses of a single neuron. For example, the linearly separable dataset is easy to split with a straight line. The XOR dataset demonstrates a limitation because no single line can separate the classes correctly. And the noisy blobs dataset shows how random variations make classification less perfect. This function acts like the data generator for experiments. By switching the dataset, learners can see firsthand how the decision boundary changes and why more complex networks are sometimes needed. Here, the prepare dataset method is filled out to actually generate the different types of datasets. 3 options are handled. Linearly separable. 2 groups of points are created on opposite sides so a straight line can divide them perfectly. XOR, not separable. 4 clusters are placed in a cross pattern so no single line can separate the classes correctly. This is the classic problem that shows why more than one neuron is needed. Blobs, noisy. 2 clusters of points are created with a lot of overlap, adding randomness that makes the classification harder. Each dataset is built using random numbers. then combined into input features X and labels Y. This makes the visualization flexible. Users can switch between simple, tricky, and noisy cases to see how the neuron's decision boundary responds. Think of it like training a student, first with easy questions, then with impossible ones, and finally with messy, confusing ones. It shows both what the single neuron can do well and where it reaches its limits. To make the plots display neatly, limits for the X and Y axes are set based on the dataset. The code finds the smallest and largest values in the data points, then expands those bounds slightly so everything fits comfortably within the graph. By calculating these limits dynamically, the display always adjusts itself to the dataset being used. This means whether the data points are spread out, tightly clustered, or noisy, the graph will zoom to the right scale without cutting anything off. It's similar to taking a group photo. Instead of keeping the camera fixed, you adjust the zoom so everyone is visible in the frame, no matter how close or far apart they are. Here we define accessor methods for the weights and bias in the 2D classifier. Each function simply returns the current value of one parameter, W1, W2, or B. These values are pulled directly from the spin boxes that the user adjusts. Having these small helper methods makes the code much cleaner. Instead of reaching into the spin boxes every time we need a value, the rest of the program can just call W1, W2, or B to get the current numbers. Think of it like having a digital display on a machine. You don't need to open the panel and read the wiring. You just look at the screen to see the value you want. These accessors give that same convenience in the code. In this part of the code, two utility methods are added: setDefaults and randomize. The setDefaults method assigns consistent starting values to the weights and bias. This gives learners a stable baseline to begin exploring how the classifier behaves without worrying about random variations. The randomize method, on the other hand, generates new random values for the weights and bias. This mimics how neural networks are usually initialized in practice, with random starting points before training begins. Each time randomize is called, the classifier will draw a new decision boundary, letting learners see how different initial conditions can affect the results. You can think of it like a lab experiment. The default button resets the equipment to a clean setup, while the randomize button shakes things up to test new conditions. Together, they make experimentation both predictable and dynamic. Now we add the update plot method for the 2D classifier. Just like before, it starts by clearing the old graph so every update shows a fresh view. Then it loads the dataset inputs and labels, which will be used to draw the points and decision boundary. This setup is essential because the classifier needs to recalculate and redraw whenever something changes, whether that's the dataset, the weights, or the bias. Without clearing and reloading, the plot would quickly become cluttered and confusing. You can imagine this like a chalkboard in a classroom. Each time a new problem is worked out, the teacher wipes the board clean before drawing again. That way, the focus is always on the current problem, not leftovers from earlier. At this point, the classifier begins drawing the data points on the plot. The inputs are divided into two groups based on their class labels. Class 0 points are drawn in one color and labeled Class 0, while Class 1 points are drawn in another color and labeled Class 1. This visualization makes the dataset easy to understand at a glance. You can see where each class of points is located and start to imagine how a straight line might separate them. It's like plotting two different species of flowers on a chart, one in red and one in blue. By seeing their positions, you can immediately tell whether a simple boundary can separate them or whether the groups overlap too much. Here the classifier draws the decision boundary on the plot. Using the current values of W1, W2, and B, the code calculates the line that separates Class 0 from Class 1. If W2 is not close to 0, the boundary is calculated as a standard line, y equals minus W1, W2, x minus B, W2. If W1 is not close to 0 but W2 is, then the boundary is vertical, defined by x equals minus B, W1. And in cases where both weights are nearly 0, the boundary isn't meaningful, so it is skipped. This visualization shows how the neuron is trying to separate the two classes. By adjusting the weights and bias, learners can watch the line tilt, shift, or become vertical, and immediately see how well it splits the dataset. It's like drawing a fence between two groups of objects on the ground. Depending on how you place the fence, you may separate them perfectly, partially, or not at all. Finally, the classifier calculates and displays its accuracy on the dataset. It does this by applying the decision rule. If z is greater than or equal to 0, the point is classified as class 1. Otherwise, it's class 0. The predictions are then compared to the true labels, and the percentage of correct classifications is computed. That accuracy value is shown in the interface, along with the current weight and bias values. At the same time, the plot title, axis labels, grid, and legend are updated to make the visualization clear and polished. This step ties everything together. It doesn't just show the decision boundary, it also tells learners how well the neuron is performing at separating the dataset. It's like a scorecard that instantly shows whether your adjustments made the classifier smarter or less accurate. The main window hosts both demos. The main function builds and launches the app. The if name equals main block is Python standard entry. Right-click inside that block, select Run. PyCharm launches the app so you can explore neurons and decision boundaries interactively. This window is the home base. We will first tour the Single Neuron 1D tab and then the 2D Linear Classifier tab. Next steps explain every control and chart element. At the very top of the interface, you can see two tabs, Single Neuron 1D and 2D Classifier Linear. Each tab gives the learner a different perspective on how neurons and classifiers work. The Single Neuron 1D tab is focused on the basics. It shows one neuron with a single input where you can play with the weight, bias, and activation function. This helps you understand step by step how a neuron transforms an input into an output and how the activation function shapes that transformation. The 2D Classifier Linear tab takes things to the next level. Instead of just one input, it uses two inputs and visualizes a full decision boundary in 2 dimensions. Here, you can experiment with different datasets, like linearly separable points or XOR, and see how a straight line tries to divide them. This makes it clear where a single neuron succeeds and where it fails, pointing the way to why multi-layer networks are needed. You can think of these tabs like different levels of a game. The first tab is the tutorial mode, where you master the basics with a single neuron. The second tab is the challenge mode, where you apply what you've learned to more complex situations in 2 dimensions. What you see highlighted here is the activation function drop-down menu. This menu lets you choose how the neuron processes its input after applying the weight and bias. The available options are sigmoid, which squeezes values between 0 and 1, making it great for probabilities. Tan, which maps values between -1 and 1, often used when balance around 0 is useful. ReLU, or rectified linear unit, which outputs 0 for negative inputs and passes positive values directly, making it efficient for deep networks. Linear, which simply returns the input unchanged, often used in regression problems. Switching between these functions allows learners to see how the shape of the curve changes on the graph below. It's like swapping out the lens of a camera. Each one gives a different view of the same input, helping you understand the unique role each activation plays in neural networks. The section highlighted here is the weight control. This knob and its linked number box let you adjust the value of W, the weight of the neuron. Changing the weight changes how strongly the input influences the output. A higher positive weight makes the curve steeper, meaning small changes in input create big changes in output. A negative weight flips the curve horizontally, reversing the input-output relationship. On the graph, adjusting the weight is like tilting a slope. With a gentle slope, the curve changes slowly, and with a steep slope, it shifts quickly. This helps learners see how weight directly affects the sensitivity of the neuron. It's similar to adjusting the volume knob on a speaker. Turn it up, and small input signals sound much louder. Turn it down, and the same inputs barely make a sound. The highlighted section is the bias control. This knob and input box let you adjust the value of B, the bias of the neuron. The bias shifts the entire activation curve left or right along the x-axis. Unlike the weight, which changes the steepness of the curve, the bias changes where the threshold lies, the point at which the neuron begins to fire strongly. On the graph, adjusting the bias looks like sliding the curve sideways. A positive bias pushes the curve to the left, making the neuron activate sooner. A negative bias shifts it to the right, delaying activation. You can think of bias like setting the baseline for a sensor. If you add positive bias, the sensor triggers earlier, even with small inputs. If you subtract bias, the sensor needs a stronger input to react. The highlighted section is the input control. This knob and number box let you set the current value of X, which is the input being fed into the neuron. Adjusting the input lets you test how the neuron responds to different values. On the graph, a vertical dashed line shows the chosen input, and a horizontal dashed line shows the corresponding output. Together, they highlight the exact point on the curve where the neuron is operating. This makes it easy to see how changing the input moves the marker along the curve. For example, with a sigmoid activation, small inputs near 0 produce outputs around 0.5, while large positive or negative inputs push the output closer to 1 or 0. It's similar to turning a dial on a machine and immediately seeing how the output meter reacts. This control helps learners connect the math formula y equals activation wx plus b to a concrete point on the graph. Displayed here are the reset and randomize buttons, two quick tools that make experimenting with the neuron much easier. The reset button takes everything, weight, bias, and input, back to their default values. It's like cleaning the slate so you can start fresh and focus on the basics again. The randomize button does the opposite. It generates new random values for the parameters. This mimics how real neural networks usually start training, with random initial weights and biases. Each click gives you a new setup to explore how different starting points affect the curve. Think of reset as a return to baseline button, while randomize is a shake things up button. Together, they encourage learners to test, compare, and discover patterns in how neurons behave. The formula panel above the graph shows the exact equation the neuron is using, y equals activation wx plus b. What makes this panel powerful is that it doesn't just show the formula symbolically, it fills in the actual values of weight, bias, and input so you can see the full calculation in real time. This acts like a receipt for the neuron's computation. You can see each ingredient, weight, bias, and input, along with the final total after applying the activation function. By linking the numeric values directly to the curve on the graph, learners can clearly connect the math with the visual result. It's similar to checking the bill at a restaurant. The formula is the menu item, but the panel shows the breakdown, how each piece adds up, so you always know exactly how the total was computed. Down at the bottom, you'll see the equation summary panel. It shows the full formula the neuron is using. Z equals wx plus b, y equals activation z. This display serves as a bridge between the math and the visualization. On one side, you have the graph showing the curve. On the other, you see the exact equation the neuron is applying. Together, they make it clear how the inputs, weights, and bias flow into the activation function to produce the final output. Think of this like a caption under a diagram in a textbook. The curve shows you the picture, but the formula reminds you of the rule behind it. This makes it easier to connect the abstract math to the behavior you see in the plot. On the left side of the graph, you'll notice the y-axis, labeled as output y. This axis shows the range of possible outputs produced by the neuron after applying the activation function. For example, with the sigmoid activation currently selected, the outputs always stay between 0 and 1, so the y-axis runs from 0 at the bottom to 1 at the top. If you switch to another activation, like tanh, the y-axis would update to show values between -1 and 1 instead. This vertical scale makes it easy to interpret how strongly the neuron is firing for different input values. You can think of it like the volume bar on a speaker. Low values mean the neuron is quiet, and high values mean it's responding strongly. The center of attention here is the graphing area itself. This is where the neuron's behavior is brought to life visually. The horizontal axis shows the input values, while the vertical axis shows the corresponding outputs after passing through the activation function. The curved line is the activation function in action, in this case a sigmoid curve, showing how outputs smoothly rise from near 0 to near 1. The shaded plotting space makes it easy to see the full range of possible inputs and outputs. As you adjust weight, bias, or input, this graph instantly updates, letting you see cause and effect in real time. It's like watching the gears of a machine turn. You twist a knob and the output shifts right in front of your eyes. The dot on the curve marks the current input and output values. The horizontal position shows the input X, and the vertical position shows the resulting output Y after the neuron applies its weight, bias, and activation function. This point works like a moving pin. As you adjust the input, the dot slides left or right along the curve, and its height changes to show the new output. It gives you a clear visual way to connect cause and effect, the exact value you chose for X, and the response produced by the neuron. It's similar to moving a cursor along a graph in a math app. Wherever you stop, you can see the exact coordinates of the function at that point. Here, the weight has been set to 0.5, and you can see how the curve responds. With a smaller weight, the curve becomes less steep, meaning the output Y changes more slowly as the input X increases or decreases. In other words, the neuron is less sensitive. Small changes in the input cause only small changes in the output. On the graph, this looks like a gentler slope in the middle of the sigmoid curve. You can think of this like a car's accelerator pedal that has been tuned for smooth driving. Pressing it lightly makes the car respond gradually instead of jerking forward. After clicking Reset, the weight goes back to 1.0, and now the bias has been set to 0.5. Look closely at the curve. It has shifted to the left. This means the neuron starts activating earlier for the same input value. In practical terms, the threshold, the point where the neuron output begins to climb steeply, moved closer to you. With a positive bias, the neuron doesn't wait for larger inputs. It begins responding sooner. It's similar to lowering the height of a hurdle in a race. With the hurdle closer to the ground, athletes can jump earlier and more easily. In the same way, a positive bias lowers the bar for activation, making the neuron fire sooner. In this example, both the weight and the bias are set to 1.0, while the input is set to 0.5. Look at the graph. The curve is steeper than before, and the output value has moved higher, close to 0.82. What's happening is that the weight is amplifying the input, making the slope of the curve sharper, while the positive bias shifts the activation to happen earlier. Together, they push the neuron into firing more strongly, even for a relatively small input. You can think of this like pressing both the accelerator and adjusting the sensitivity of the pedal at the same time. The car responds more quickly and with greater power to even a small press. Here we return to the Reset button to bring all values back to their baseline. Resetting weight, bias, and input ensures the neuron goes back to its default state, which makes the next experiment easier to compare. Think of this as wiping the whiteboard clean before solving a new problem. By starting fresh, you avoid mixing the effects of previous changes and can see exactly how a single adjustment, like changing weight or bias, impacts the curve. Clean comparisons are the key to building strong intuition. When you know the starting point is always the same, each change you make tells a clear story about how neurons behave. This part of the interface highlights the Randomize button. Clicking it assigns fresh, random values to the weight, bias, and sometimes the input, giving the neuron a brand new configuration each time. Randomization is useful because it mimics how real neural networks usually begin training, with random starting points. Each run begins differently, which helps ensure the network doesn't get stuck always producing the same outcome. On the graph, clicking Randomize instantly redraws the curve, showing you how a new set of parameters changes the neuron's behavior. It's like rolling dice before starting a game. Every roll sets up a unique challenge to explore. Here, the neuron has been given randomized values for weight, bias, and input. Notice how this instantly changes both the slope of the curve and its position along the x-axis. A larger weight makes the curve steeper, so the transition from low output to high output happens more sharply. The bias shifts the curve left or right, moving the threshold for activation. And the input value determines where the dot is placed on the curve, showing the neuron's exact output for that choice. Together, these random settings make the neuron's behavior unpredictable, but very informative. It's like running on a track where the terrain and starting line change every time. You quickly see how flexible or limited the neuron can be in responding to different conditions. In this step, the Reset button is used again, bringing the neuron back to its baseline before switching to a different activation. Returning to this known baseline is important because it makes comparisons fair. When all experiments start from the same point, it's easier to see how much of the change in the graph comes from the activation function itself, rather than leftover adjustments to weight, bias, or input. It's like comparing runners in a race. If they all start from the same starting line, you can fairly measure who runs faster, but if one started halfway ahead, the comparison wouldn't make sense. Resetting gives every experiment the same starting line. Open the activation dropdown to compare options. Switching activation is like changing the lens that shapes how Z turns into Y. Before switching from sigmoid to tan, it's helpful to recall the main difference between the two. Sigmoid outputs values between 0 and 1, so the curve never goes below 0. By contrast, tant outputs values between -1 and 1, and its curve is centered at 0. This makes tant especially useful when signals need to be balanced around 0. Instead of all outputs being positive, tan allows both negative and positive outputs, which can make the neuron more responsive in certain network designs. Think of sigmoid as a door that only opens one way, while tant is a door that can swing both left and right. Both control the flow, but tant gives more flexibility by allowing signals in both directions. Now the neuron is using the tant activation function. Its formula is tant of z equals z minus e squared minus z, ez plus e squared minus z. On the graph, you can see it creates a smooth S-shaped curve, very similar to sigmoid, but with one important difference. Instead of being squeezed between 0 and 1, it stretches from -1 to +1. This also means the curve is centered at 0, making it symmetric above and below the horizontal axis. This symmetry makes tan useful in many cases because it balances positive and negative signals, helping networks learn more efficiently. It's like a thermostat that can both heat and cool instead of only heating, giving it the ability to push in both directions. Here, the randomize button is pressed while the tant activation is selected. Notice how the S-shaped curve changes its slope and position depending on the new random weight and bias values. With larger weights, the curve gets sharper and transitions more abruptly between -1 and +1. With different bias values, the whole curve shifts left or right, moving the point where the neuron crosses 0. The outputs still span both negative and positive values, but the balance point changes. This is like running on a track where the terrain and the starting line both shift every time. You can see how random values dramatically affect how quickly and where the neuron activates. This view compares how the tant activation behaves differently from sigmoid, even when using the same weight and bias. With tan, the outputs are centered around 0 and spread between -1 and +1. This makes the curve symmetric with plateaus at both the top and bottom. In contrast, sigmoid always squeezes outputs between 0 and 1, never going negative, so its curve is shifted upward. The practical effect is that tan allows the neuron to represent both positive and negative signals, which can balance the flow of information in a network. Sigmoid, however, is limited to only positive outputs, which sometimes makes training slower. It's like the difference between a scale that measures weight only in pounds, always positive, and one that measures both gain and loss in weight, positive and negative. The second gives a fuller picture. We now click the Reset button to return everything to a clean slate. This prepares the interface for the next big step, exploring the 2D classifier. Resetting clears away any leftover adjustments from the tant activation, ensuring we start fresh. That way, when we move into the 2D view, we can focus entirely on the new concept without old settings interfering. It's like wiping the chalkboard after finishing one lesson, so the board is ready for the next topic. Clean comparisons help keep insights clear and easy to follow. By clicking the 2D Classifier Linear tab, we move from working with a single neuron in one dimension to a classifier that works in 2 dimensions. In this view, you will see data points plotted on a plane, representing 2 classes. Alongside the points, the classifier will attempt to draw a straight decision line that separates the 2 classes as best as possible. This step introduces the idea of a decision boundary in machine learning. Instead of just showing how a neuron transforms numbers into outputs, it now shows how a neuron can separate categories of data in space. It's like drawing a chalk line on the ground to divide 2 groups of objects, apples on one side, oranges on the other. the classifier tries to find the best line that makes this separation clear. This is the 2D classifier control panel. Here, you have everything you need to explore how a linear classifier works. At the top, you can choose different datasets, like linearly separable points or more challenging ones. Below that are sliders for W1 and W2, which are the weights for the X and Y axes, and a slider for the bias. These let you adjust the position and angle of the decision line. You also have reset and randomize buttons to quickly return to a baseline or test new random values. The accuracy readout tells you how well the current line is separating the classes. Finally, the plot shows two groups of points, each color-coded by class, and a straight line, the decision boundary that the classifier is using to try and separate them. It's like watching a referee draw a chalk line across a field to keep two teams apart. The weights and bias control the slope and position of that line, while the accuracy score tells you how fair and effective the split is. At the top of the panel, you can select different datasets to test the 2D classifier. Each dataset highlights a different challenge for the decision boundary. Linearly separable, two clean clusters that can easily be divided by a straight line. XOR, not separable, points arranged in opposite corners where no single straight line can separate them. This shows the limits of a linear classifier. Blobs, noisy, clusters with added randomness, creating overlap so the decision line is less perfect and accuracy drops slightly. Switching between these datasets helps you see both the strengths and weaknesses of a single neuron. It's like practicing on different terrains: flat ground for easy separation, a checkerboard for impossible separation, and bumpy ground with noise for messy, real-world challenges. This control adjusts W1, which is the weight on the x-axis input. Changing W1 directly affects how the decision boundary tilts. When you increase the absolute value of W1, the line rotates, becoming more sensitive to changes along the x-axis. Decreasing it flattens the influence of X, making the line less responsive to left-right movement. You can think of this like tilting a clipboard. A steeper tilt makes objects slide off quickly when moved side to side, while a gentle tilt makes the movement slower and less pronounced. In the same way, W1 determines how strongly the classifier reacts to shifts along the horizontal direction. This control adjusts W2, the weight on the y-axis input. Changing W2 rotates the decision boundary in a different direction compared to W1, making the classifier more or less sensitive to up and down movement in the data. Together, W1 and W2 work like steering controls for the decision line. W1 tilts the line left or right, while W2 tilts it up or down. By balancing the two, you set the overall orientation of the boundary. It's similar to adjusting the handles of a seesaw. One handle changes how it tips side to side, the other changes how it tips front to back. Combined, they control the full angle of the board. This control changes the bias B, which shifts the entire decision boundary line up or down without changing its tilt. Think of it like sliding a fence parallel to itself. By moving the fence, you include more points from one side and fewer from the other, adjusting how the classifier divides the two classes. While weights W1 and W2 control the angle of the line, the bias simply repositions it. Together, all three, W1, 2, and B determine the final placement of the decision boundary. The accuracy on dataset readout shows the fraction of points that the classifier has correctly predicted. Right next to it, you can also see the exact equation of the current decision boundary, including the values of W1, W2, and B. Together, these two pieces of information let you evaluate how well the line is separating the classes, both by the numbers and visually by looking at the graph. Think of it like grading a test. The accuracy percentage is the score, while the boundary equation is the step-by-step solution showing how the answer was reached. You can judge performance by either one, but using both together gives the clearest picture. The blue line you see on the chart is the decision boundary for the 2D linear classifier. This line represents the exact places where the model is undecided. Points that fall right on this line could belong to either class. On one side of the line, every point is predicted as class 0, and on the other side, every point is predicted as class 1. In this simple model, the which side of the line rule is the entire decision process. Think of it like a referee drawing a chalk line on a field. Players on the left are one team and players on the right are the other. The line itself is neutral, and all the model does is separate the teams based on which side they're standing on. On this graph, the blue points represent class 0 and the orange points represent class 1. These markers identify the two groups of data that the classifier is trying to separate. Your goal is to rotate and slide the decision boundary line so that most of the blue points fall on one side and most of the orange points fall on the other. It's similar to drawing a border between two zones on a map. The line doesn't change the points themselves, it only defines which region they belong to. Adjusting weights and bias is like redrawing that border until it best separates the two groups. Now the Randomize button is used while the dataset is set to linearly separable. Each time you click Randomize, the classifier gets new random weights and bias, which changes the slope and position of the decision line. Sometimes the random line will do a good job separating the two clusters. Other times it may fail and cut through the points incorrectly. That's because random parameters are not guaranteed to produce the perfect boundary. This mirrors how real neural networks start with random values before training adjusts them to perform well. You can think of it like drawing a fence across a field blindfolded. By chance, the fence might separate the groups nicely, or it might not. Training is what later corrects and fine-tunes these boundaries. The results panel shows the accuracy of the classifier. High accuracy means the decision boundary is doing a good job keeping the two clusters separate. Low accuracy means the line is cutting through a cluster, misclassifying points. In this example, the accuracy is only about 57%, which means many points are being classified incorrectly. To improve this, you can adjust the weights W1 and W2 to change the tilt of the line, and adjust the bias B to slide the line up or down. Think of it like repositioning a fence between two groups. If the fence cuts right through one group, the separation is poor. But if you tilt and slide it until one group is mostly on one side and the other group on the other side, the accuracy improves. In this step, you click the Reset button to return everything to the default settings before moving to the next dataset. Resetting ensures the weights and bias go back to their baseline values, which makes the next experiment easier to understand. Using a consistent starting point is important. It helps you clearly see how changes in W1, W2, or bias affect the decision line when you switch datasets. Without resetting, leftover adjustments from the previous test could make the results confusing. It's like starting every race from the same starting line. You know that any difference in results is due to the runner's performance, not because one runner started ahead. Now we switch to the XOR dataset, which is labeled as not separable. Unlike the linearly separable dataset, where a straight line could cleanly divide the two clusters, XOR has its points arranged in diagonal corners. Because of this layout, no single straight line can separate both pairs of classes at the same time. If you try to draw a boundary through one pair, the other pair ends up misclassified. It's like trying to divide a checkerboard into black and white squares with just one straight cut. You can't cover both diagonals at once. This example shows the limitation of a linear classifier and why more complex models are sometimes necessary. Here, the Randomize button is used while the dataset is set to XOR. Try clicking it a few times. You'll notice that no matter how the weights and bias are randomized, the decision line can never fully separate the two classes. The line might get one diagonal pair correct, but it always fails on the other pair. That's because XOR is fundamentally not linearly separable. A straight line simply isn't powerful enough to capture the pattern. This limitation is important. It motivates the need for more advanced models that can use nonlinear features. In practice, stacking multiple neurons or adding nonlinear activation functions allows networks to solve problems like XOR that a single linear classifier cannot. It's like trying to cut out a circle using only straight cuts. You can approximate, but you'll never get it perfect without curved tools. Here are the results for the XOR dataset. Notice that the accuracy stays low, around 41% in this example. That's because a straight line can't capture the checkerboard pattern of XOR. No matter how you adjust W1, W2, or the bias, the decision boundary will always leave large groups of points misclassified. This demonstrates a key limitation of linear models. They can only separate data with straight lines. For complex patterns like XOR, you need either multiple neurons working together or engineered nonlinear features to carve out more flexible decision regions. It's like trying to cut a circle with a single straight slice. You'll never outline the shape correctly. To solve it, you need more slices or curved tools, just as networks need more complexity to capture nonlinear patterns. This dataset is called blobs noisy. It introduces controlled overlap between the two classes, which simulates the kind of messy, imperfect data you often see in the real world. With this dataset, sometimes the decision boundary works well and sometimes it struggles. That's because the added noise means the two classes are not perfectly separated. Some points from each class will always be mixed in with the other. This example shows that in practice, accuracy can vary, even with the same model. It also highlights why models in the real world must learn to handle noise and uncertainty rather than expecting perfectly separable data. It's like trying to draw a line between two crowds of people at a festival. Most of them cluster on their side, but a few wander into the other group, making the split less precise. This is the blobs noisy dataset. It adds controlled randomness and overlap to simulate messy, real-world data. When you click Randomize, the positions of the points shift slightly and the line tilts depending on the new random weights and bias. Sometimes the classifier does a good job and accuracy rises. Other times, the overlap makes separation harder and accuracy drops. This is great practice for tuning W1, W2, and B to squeeze out more performance when possible. You'll see that in noisy situations there is no perfect line, only better or worse fits. It's just like drawing a divider between two crowds of people in a busy marketplace. Most people will group together on their side, but some wander over and mix with the other crowd. The challenge is to place the divider so that it works as fairly as possible. These are the results with the blobs noisy dataset. When the noise is low, a well-placed line can achieve high accuracy because most of the points from each class cluster cleanly on their side. But as the noise increases, the overlap between the classes grows. At that point, even the best possible straight line will leave errors behind. Some points from class 0 will end up on the class 1 side and vice versa. This demonstrates the trade-off between model capacity and data complexity. A simple linear classifier can handle clean separations, but real-world data is often messy and overlapping. In those cases, more advanced models with additional neurons or nonlinear features are needed to better capture the patterns. Think of it like drawing a fence in a windy field. If the groups are far apart, it's easy to place the fence. But if the groups are all mixed together, no straight fence will get it perfect. Great work. You have completed the tutorial. You learned how a single neuron takes an input, applies a weight and a bias, and produces an output. You also saw how a linear classifier can draw a decision boundary in 2 dimensions. You practiced with 3 types of datasets. First, the linearly separable dataset, where a straight line works perfectly. Second, the XOR dataset, where no straight line can solve the checkerboard pattern. Third, the noisy blobs dataset, where overlap and randomness make separation imperfect. The key lesson is this: linear models are simple and effective when the data is clean, but they fail on nonlinear patterns and they struggle with noisy data. That is why more advanced models with nonlinear features and multiple neurons are needed in real applications. Thank you for completing the tutorial.